Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about the Hall effect. The Hall effect is an effect with magnetic fields acting on moving charges that, among other things, allows us to determine whether positive or negative charge carriers are carrying current through a device. It also allows us to actually measure the magnetic field strength. So you can make a Hall probe if you need to figure out what is the magnetic field strength for a given region. So let's get into how all of that works. Before we can get into the physics of the Hall effect itself, we need to recall a few things that we've learned in previous lectures. For example, we know that the force on a moving charged particle from a magnetic field is given by the equation F equals QV cross B, or in other words, the magnetic force on this moving charge has a magnitude of QVB times sine of whatever angle is between the field and the velocity vector. And in a like manner, if we wanted to get the force of an E field, so for the magnetic field it's this, for an electric field, if we want the electric field on a charged particle, moving or otherwise, then that is going to simply be F sub E is QE. In fact, that is the entire point of the electric field and the magnetic field. That means that the magnitude of the force from the electric field is simply Q, the charge, times E, the electric field strength. There's maybe one other thing that we might recall, but that one's a little bit more complicated. That has to do with how much charges get moved across, in the microscopic view, a current-carrying conductor. And that was that the current is given by the density of charge carriers times the charge of each carrier times the drift velocity of these charge carriers, the average drift velocity, times the cross-section area of the conductor through which all these are traveling. This one right here really is kind of important for completionists. If you wanted to figure out how to use the Hall probe, you'll recall that from the macroscopic view, that this became Ohm's law. That is, delta V is IR, or in other words, the current is the voltage drop divided by the resistance. And perhaps one last little thing is the relationship between E field and voltage drop. And that is that the voltage drop is equal to the electric field strength dotted with the displacement vector, negative E dot D. Now, how do all these things play into the Hall effect? All right, suppose I have, let's say, a wire, and maybe the wire is oriented left to right like this. And suppose that in addition to this wire, I have locally a magnetic field. I'm going to draw the magnetic field as being basically uniform and oriented out of the screen towards you, the viewer, and really towards me as well as I make this. All right, so these circles with dots, these all represent for us a magnetic field. Now suppose that I run a current through this wire. You'll recall from our discussion of current that if I want to have a current running from, let's say, left to right, so let's say that I have a current I that happens to be in this direction in the wire, hypothetically. That means that I can either have negative charges moving right to left, or I can have positive charges moving left to right. Okay, so this is These are the ways that I can create a current that is from left to right. Let's say now, for the sake of argument, that I happen to have a negative charge to create this current. So this negative charge is moving in this direction on average. That's your drift velocity. All right, what direction does the force from the magnetic field act on this particle? Well, basically you should be using the equation that we started with, QV cross B. Got to remember that Q is negative, so we basically use our right hand, which I have to use actually my left hand because of the way the mirroring works. This is my right hand, this is my left hand. You should use your right hand. This should look like a right hand to you based on how my setup is. Okay, I have a particle that is moving from left to right like this. And now my field is pointing out of the board kind of away. So my field is pointing away from you. That means that we should be getting a force that is, for a negative particle, that force should be pointing in the upward direction for positive, and therefore the downward direction for a negative. So this hand actually is correctly giving me the direction of the force on this particle. So this is the direction of my force. All right, so suppose instead I have a positive particle. Note that I've flipped the sign of the particle, and I've also flipped the direction that the particle is moving in. This means that I should actually expect the force to be in the same direction as with the negative particle. Let's check with our right hand. So I have my particle, and it's moving in this direction. I have the curl, I have the B field pointing out towards you. My thumb points downward. So this one, again, has a force in the downward direction like so. So in both cases, the magnetic field exerts a downward force. Okay, that means that both moving negative charges and moving positive charges will tend, in this scenario of a current that is from left to right and a magnetic field pointing out of the page at you, both will tend to accumulate at the bottom of this wire as opposed to at the top. And that means that if I apply a voltage probe between top and bottom, I should get a voltage. So again, if I were to say, all right, I want to measure voltage between, say, this part of the wire and that part of the wire, delta V. And if I wanted to measure a voltage between the top and the bottom of the wire, delta V. And let's say that I happen to put the leads oriented in the same way for both of these. Okay, so maybe I have my common black lead here. So this is the common, and then this is the sort of like delta V red. This guy right here will read out as greater than 0. It'll be a positive voltage. And this guy right here will read out as negative. It'll be a negative voltage. So if I just hook up a voltage probe between the top and bottom of this wire and run current through it, then I can get either a positive or a negative, and that tells me whether my charge carriers are predominantly the negative charges or the positive charges. So that's kind of a cool discovery. It means we can measure it for most materials. It turns out that for most metals, it's the negative charges. For a lot of semiconductors, it's actually the positive charges, for what it's worth. Now, there's other applications than just figuring out whether it's a positive or a negative charge that essentially is carrying the current. Let's say that instead of a wire, I have a sort of sheet, and maybe it's a metal sheet, so I know that it's negative charges, or I know it's positive charges or whatever. I think that a lot of them use semiconductors, so I think maybe a lot of them are using positive charges. That's kind of irrelevant. If I have a sheet like this that I have the ability to hook up sort of like two things to, then I could in principle actually use this to measure a magnetic field strength. The idea is this. Let's say that I happen to hook this side up to a voltage source. Okay, so I have just like a plus and minus voltage source, a battery, for example. Maybe I should just draw a battery in here, like so. Okay. The result of having this battery is that I expect now there to be a current. The current should run in this direction. Okay, that means that if I have a negative charge down here, let's say, then it's going to be moving in this direction. Now, let's say that I happen to place it again in a magnetic field. All right, so I've got current, I've got my charge moving, I've got my magnetic field, and I can even essentially like figure out what direction the force acting on this moving charge should be in. So I could have basically a force in this direction due to my magnetic field as this charge moves. And so this charge should move over here like this. Now, if that were to occur, then by applying a second set of probes, basically connected to this side and to this side, if I were to apply a voltage drop here, a second voltage, I would be able to measure a voltage drop. Okay, so what we do is we instead apply a bias voltage. So we'll call this, so suppose that we apply a bias voltage across this sheet like I've drawn here. Okay, this bias voltage will then apply an electric field across the sheet. From the positive to the negative direction. So this is now like my bias E field. Okay, what that will do is it will apply a force on this charged particle in the opposite direction. We'll say this is F sub E. It's in the opposite direction as the magnetic field has been applying the force. So these two forces can now kind of fight over which direction it's going to make the particle go. And so if I have that the FB, the magnetic field force, and FE, the electric field force, are in opposite directions but equal magnitude, then net force on this particle will be 0. So particle doesn't deviate. All right, so I apply some bias voltage. Particles therefore do not deviate. And maybe I also connect a voltage probe to measure what's the actual voltage between the two sides of this thing. So I know that I'm applying a bias voltage, and then I have a probe that tells me what is the actual voltage drop. Now, if I were to have the bias voltage balanced to where no charges move onto one side or the other of the plate, then whatever the bias voltage is that I've applied will also be the voltage measured by the probe. If I have too much bias voltage or too little bias voltage, then the probe voltage will differ from the bias voltage. And the result of that is that I will basically have moved particles to one or the other side of this sheet. And therefore, that's what's causing us to have a difference between the bias voltage and the measured voltage. So if I get the bias voltage to be equal to the measured voltage, we could call that the Hall voltage. Then it means that I also have balanced these two forces. And the condition for these to be balanced is that the charge times the speed at which this particle is moving times, and that speed is the drift speed, so charge times drift speed times magnetic field strength should equal charge times electric field strength, which is in turn charge times this Hall voltage divided by the distance, the actual length distance between the two sides. All right, so now I can kind of solve this for the magnetic field strength. And that magnetic field strength B, if I divide out the Q from both sides, I end up getting E over drift speed, which is the delta V that is measured, the Hall voltage, divided by the speed times the length. And this drift speed in turn can be found by using Ohm's law to get the current, delta V over R. Okay, so current is this delta V, you could call this like delta V sub 1 or whatever, delta V, divided by the resistance from one end to the other. So this whole thing basically has resistance R. All right, so in turn, the drift speed you can get by rearranging the equation for the microscopic view to get that the drift speed is equal to the current divided by the density of carriers times the charge times the cross-section area. So the cross-section area in this case would be basically like the cross-section of this end here. Yeah, the density of carriers, little n, that is going to depend upon what the material is made out of for the most part. Essentially, that ends up being a function of the actual density, like mass per unit volume, times essentially like how many free carriers are there per mole, let's say, of the material would be one way of getting that. And that's a little bit more complicated. Usually that is a given parameter. Maybe you have, let's say, like one free carrier per atom for a good conductor like copper as a good estimate. And so you can then figure out how many atoms by getting the molar mass and by getting the actual density. Q in this case would represent the particle charge. So Q would be essentially the elementary charge of the particle. Okay, so if you put all those things together, then you're able to measure the magnetic field strength of the magnetic field that you've put this Hall probe into. So that's all for today. Well, thanks for joining me, and hopefully you learned a lot from this. See you in the next one.